Looking down at our planet from orbit, it is easy to assume we have arrived. The continents are wrapped in artificial light, making us look like a highly advanced species. But in the timeline of the cosmos, we are barely beginners. Every major leap in our development directly correlates with finding a denser, more efficient way to power our tools. We replaced human and animal muscle with machinery by combusting coal to boil water. We wired entire continents together, distributing electrons across vast grids to drive heavy industry and illuminate the night. We eventually learned to extract the binding energy of the universe itself, splitting the atom to generate millions of times more heat per gram than any fossil fuel. Human history is a thermodynamic ledger. Our growth is dictated entirely by our escalating consumption of energy. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a method to categorize civilizations. Instead of guessing at their politics or biology, he looked exclusively at their energy diet. He defined a Type 1 civilization as a planetary society, a species capable of harnessing all the energy that reaches its homeworld from its star. A Type 2 civilization steps up to the stellar scale. They capture the total energy output of the star itself. A Type 3 civilization commands the energy budget of an entire galaxy, controlling the output of billions of star systems. This scale is an objective thermodynamic yardstick. It sets the absolute physical limits for what any intelligent species can theoretically achieve. So, looking back at our own planet, where do we land on Kardashev's scale? We don't even make the list. We fail to meet the baseline energy requirements for a Type 1 civilization. Astronomer Carl Sagan recognized that civilization development is a continuous spectrum. Moving from a primitive society to a planetary one requires intermediate measurements. This is Sagan's continuous Kardashev equation, calculating the exact decimals between tiers using a civilization's raw energy consumption. Based on machine learning forecasts, global demand will reach 887 exajoules by 2060. Plug those numbers in, and humanity scores a 0.73. Scoring a 0.73 creates the impression that we are most of the way to becoming a planetary civilization, but that number hides a massive terrestrial illusion. Being a Type 0.73 civilization does not mean we are 73% of the way to Type 1. This chart shows the reality of logarithmic scaling. The energy required multiplies exponentially between every decimal point. Take humanity's current infrastructure, producing roughly 20 terawatts. A Type 1 civilization requires 10,000. Compared to that threshold, our modern infrastructure is a rounding error. We cannot bridge this gap by simply building more coal plants. Moving from 0.73 to 1.0 requires shifting from burning stored geological fuel to capturing the total energy flux of the planet itself. This means mastering technologies like commercial nuclear fusion and global-scale carbon capture, while managing the massive heat waste that such energy production generates. At our current rate of growth, it could take another 1,000 years to bridge that gap. What specific planetary engines and global systems will we have to build to actually survive that climb? Humanity currently sits just below the first major threshold on the Kardashev scale. Graduating to this level depends on planetary-scale management. It is a transition away from simple energy extraction and toward the active maintenance of the systems that support us. When Carl Sagan formalized the Kardashev scale, he calculated the Type 1 threshold based on the planet's total energy output, 10 to the 16th watts. Building a global architecture capable of supporting billions of people requires a level of logistical resilience humanity has never before attempted. We are moving toward a state where our infrastructure must function as a single, integrated machine. Our energy demand is surging. Since the Industrial Revolution, global energy consumption has followed a consistent growth trajectory of 1 to 2 basic needs. This disparity creates a difficult transition. To uplift the global population, we must generate massively more power, while simultaneously dismantling the fossil fuel foundation that currently provides 80%. Reaching the threshold requires us to integrate these systems into a unified whole. Integration requires us to move power beyond local borders, building continental and eventually planetary transmission networks. This infrastructure functions as a smart grid, capable of instantly balancing electrical loads and routing power across oceans to meet demand. A global network allows us to harness intermittent renewables, like wind and solar, and deliver that energy to exactly wherever it is needed. This unified nervous system allows a planetary civilization to function without localized failures or blackouts. Forecasts from machine learning models identify a major obstacle in this progression, the sustainability bottleneck. As economic growth and population rise, our energy demand collides with the Earth's physical limits. We measure this tension by comparing our ecological footprint against the planet's biocapacity. Surpassing this threshold means our demand exceeds the Earth's ability to regenerate, causing a progressive failure of the systems required to sustain human infrastructure. Reaching Type 1 is therefore a test of balance. A civilization must master the management of its biosphere to survive the transition. By analyzing our current technological and economic trends, we can forecast our civilizational progress through the middle of this century. Based on current trajectories, global energy consumption is projected to reach 887 exajoules by the year 2060. On the Kardashev scale, this energy output puts humanity at a value of 0.7449. At this current rate of growth, reaching a full 1.0 would take millennia. Type 1 remains a theoretical benchmark rather than an inevitable destination. Bending this curve requires a shift in how we manage our environment. Sustainability is the requirement for scaling. Breaking the bottleneck depends on breakthroughs like nuclear fusion, which offers a path to significant energy production without the environmental costs of fission or fossil fuels. Fusion, combined with a unified global grid, provides the sustainable power required to support a growing civilization while staying within planetary boundaries. By unifying the grid and respecting these physical limits, humanity secures its home cradle. A perfected planetary machine enables the next transition. The energy required to move beyond Type 1 lies waiting in the star we orbit. Past our own atmosphere, Earth quickly recedes into the dark. What remains is a continuous, roaring fusion reaction that dwarfs our entire planetary existence. Reaching the status of a Type 2 civilization does not require a species to manually ignite or manipulate the stellar fusion. It requires the engineering capacity to capture the total energy output that the star is already projecting into the void. The difference in scale between drawing power from a planetary crust and harvesting it directly from a star is difficult to conceptualize. Our current civilization extracts energy from chemical bonds, wind currents, and localized nuclear decay. A star offers an unceasing torrent of raw radiation. This logarithmic scale visualization shows Earth's current total global energy consumption as a single point of reference. The expanding column represents the sun's output, which is hundreds of billions of times greater. Any civilization relying exclusively on the resources of its homeworld eventually faces a strict mathematical boundary. Biological and industrial growth demand energy, and a single rocky planet receives only a fraction of a billionth of its host star's light. Remaining bound to planetary resources enforces a strict cap on development. Until a species bridges the gap to harvest its star directly, its population and technological capacity are permanently constrained by the limits of one fragile biosphere. The theoretical megastructure required to capture that escaping stellar energy was popularized by 20th century physicist Freeman Dyson. In the decades since he introduced the concept, science fiction has largely depicted it as a rigid, solid shell built to entirely enclose a star. From an engineering standpoint, a continuous solid sphere is simply structurally impossible. A rigid object of that sheer size experiences overwhelming gravitational shear forces, pulling the structure inward until it fractures and collapses into the star. To prevent the shell from breaking apart, a civilization needs materials with infinite tensile strength, removing this from actual engineering. Furthermore, dismantling every planet and asteroid in our solar system falls drastically short of the mass required to construct a solid sphere. The solid shell is a myth. It is a persistent misunderstanding distracting from the highly practical, physics-compliant megastructure that an expanding civilization would actually build. The mathematically sound approach is the Dyson Swarm. It is a dense, highly orchestrated network of trillions of independent orbital bodies encompassing the star. Construction is entirely incremental, beginning with a single autonomous solar collector in strategic orbit. Powered by that first unit, hundreds more are launched, expanding the array. To maintain stability, units operate on staggered, three-dimensional trajectories, avoiding collisions and shadows. By spacing these elements out over tens of millions of miles, the swarm maximizes its total surface area, catching an ever-increasing percentage of the star's escaping radiation. However, capturing radiation is only one function of the network. As energy capacity grows, the swarm incorporates massive rotating habitats. These artificial biospheres, constructed from processed asteroid material, are woven directly into the orbital network to house expanding populations. The outer, colder orbital layers provide ideal conditions for stellar-scale computing nodes. These massive processors utilize the abundant energy to run highly complex simulations and digital architectures. Between the habitats and the computing nodes lie industrial zero-gravity facilities, using concentrated sunlight to process raw materials and transmute elements on the fly. Communication relays link these disparate elements, passing data and redirecting energy beams instantaneously across the vast distances of the network. A completed Dyson Swarm operates as a distributed, star-sized artificial habitat. It completely reorganizes how a species lives, moving them from the surface of a single rock into a customized high-energy orbital ecosystem. Getting to that final state requires overcoming a severe logistical bottleneck. Constructing a swarm of this magnitude cannot be launched from the bottom of Earth's gravity well. The fuel costs for chemical rockets would quickly outpace the energy returns. A civilization must first establish space-based scaffolding. This means building permanent orbital infrastructure, shipyards, and launch loops that allow for heavy manufacturing outside the atmosphere. Raw materials are sourced entirely from the vacuum. Fleets of autonomous mining drones strip near-Earth asteroids and dead moons for metals and silicates, leaving the planetary ecosystem completely untouched by the industrial process. A Type 2 civilization is built by autonomous, self-replicating space industries. The primary role of the biological species is simply to invent the machines that do the heavy lifting. Every step of this process relies strictly on known physical laws. Constructing a Dyson Swarm requires no new physics, no faster-than-light travel, and no artificial gravity. The true barriers to entry are scale, time, and industrial manpower. It is a matter of civil engineering projected onto an astronomical canvas. Because of this scale, the construction is not a single, coordinated project. It is a slow, multi-generational evolution driven by long-term resource demands. The initial stages might begin within a single century, marked by a few scattered satellites beaming microwave energy back to orbital refineries. From there, populations and robotic fleets double at regular intervals. Even at highly conservative growth rates, it takes tens of thousands of years for the swarm to multiply enough to slowly obscure the star's visible light. Accessing the full output of a star eliminates resource scarcity. With nearly infinite power available, the physical constraints on a civilization's territorial reach evaporate. Travel transforms from slow, linear planetary missions into exponential interstellar colonization. The swarm provides the raw energy needed to push colony ships via heavy lasers to a fraction of light speed, aiming them at neighboring stars. Once a civilization successfully harnesses its home star, it has the energy and the infrastructure to repeat the process on the next star over, and then the next.